Guys, so this is electron configuration part 2. You definitely need a periodic table. If you have not printed a periodic table at this point, I would highly encourage it. You're going to need it for pretty much every single unit that we do for the rest of this year. So imprint that periodic table. Okay guys, so I'm going to start this class with a little review from last class, and we're going to write the electron configuration for the following elements. So I made myself a little bigger so you can follow along. So we are writing the electron configuration for calcium. It is in the 4th period on our periodic table. So there it is, number 20. All right, so we always start from the beginning and go left to right, top to bottom when writing our electron configurations. So let's go ahead and start. So first things first, we're supposed to write the electron configuration from calcium. So first thing, first energy level. So that's the first part of our configuration. 1. Ooh, my handwriting is going to be rough. All right. Let me try that again. Sorry, guys. Try it again. So 1. All right. And then what sub-level are we in? We're in the S. How many? Oh my goodness, this is not going well. 1S, and then how many boxes do we cross? 2. All right. All right. So 1S2, and then we've gone all the way across the first level. So now we go on. We are in the second sub-level, second energy level, S sub-level, and we cross 2 boxes there as well. So then our next part would be 2S2. Keep moving on over on our periodic table, end up on the second energy level still in the p orbital, and we cross 1, 2, 3, 4, 5, 6 boxes. So we have 2p6. Then our third energy level here, S sublevel, and we cross 1, 2 boxes, 3s2. Keep moving left to right. We're in our p orbital now. So third energy level still, p orbital, and we cross 1, 2, 3, 4, 5, 6 boxes, so 3p6. And then finally we're almost there, 4th energy level, S sublevel, and we cross 1, 2 boxes. So our final configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. And that's our configuration for calcium. So our next configuration that we need to do is molybdenum. I don't actually know if that's how you say it, but that's how I say it. So molybdenum is right here on our periodic table. It is number 42. So this time we have S, P, and we're going to have the D sublevel in there as well. All right. So as always, we start at the beginning of our periodic table, left to right, top to bottom. We read our periodic table the same way we would read a book. All right, so first energy level, S sublevel, and we cross 1, 2 boxes. Second energy level, S sublevel, 1, 2 boxes. Keep going. 2 P sublevel, 6 boxes. Third energy level, S sublevel, cross 2 boxes. Keep moving, still on the third energy level, in the p orbital, and we cross 6 boxes there, so 6 electrons. And then we have all down here, so we're in the 4, the S sublevel, we cross 2 boxes, and then we get to our D sublevel here. So guys, remember, anytime you're in the D sublevel, it's always 1 energy level down from the row you're on. So if I'm on the 4th row, this is going to be 3D, and I'm going to cross all 10 boxes on my D sublevel. All right, after I've crossed that, I'm now in my P orbital. P orbital is the same as the row number. So 4, go back up to 4, and we cross 6 boxes there. So 4p6. Then come over here. We are 5 S sublevel, and we cross 1, 2 boxes. And finally, last but certainly not least, we have our 4D, because remember, once again, D sublevel is one row down. We are crossing 1, 2, 3, 4 boxes. So 4D, 4. Boom. So hopefully that was a helpful little reminder over electron configurations for y'all. I'm going to make my camera smaller again. All right. So there are some exceptions. Wah, wah. I know, not fun. But there are 2 exceptions to electron configurations that you do need to know. So the first one is group 6 in our transition metals, which just so happens to be chromium, molybdenum, and tungsten. So what's going to happen is they are going to move 1 electron from the S sublevel to their D sublevel. So this gives them a half full D sublevel, which is just a little more stable. So what's going to happen in our configuration? So what it would normally look like is we would have whatever energy level we're on. I'm just going to put X, S2, and then in D4. But what's going to happen is one of those S sublevel electrons is going to move to the D sublevel. So really our electron configuration then becomes whatever energy level we're on, just representing it with an X. S1, and then in D5. And again, N is just representing whatever sublevel we're on, or energy level. Sorry, guys. So this gives it just a more stable half full sublevel. So our previous practice problem that we just did with molybdenum does count as an exception. So let's go ahead and fix it really quickly. So instead of it being 5S1 or 5S2, it's going to be 5S1. And 4D5. Okay, group 11, which is copper, gold, and silver, is going to be pretty much exactly the same. It's still going to move, so group 11, copper, silver, and gold, is going to move an electron from the S to the D sublevel, and it's going to give it a full D sublevel, which makes it much more stable. So it would look like XS2, and then whatever sublevel D9, but it's going to move one of those from the S sublevel, so we end up with XS1 in D10. Again, these numbers are just representing whatever energy level they're on, the X and the N. All right. So now then, we're going to talk about our next type of an electron configuration, and that is noble gas or abbreviated configurations. So let's look at our configurations up here. You guys see, like for calcium and molybdenum, our configurations all start the same. 1s2, 2s2, 2p6, 3s2, 3p6, so on and so forth. So guys, that's a lot to write. So we have an abbreviated version, and that's noble gas, or sometimes it's also just called abbreviated version. And with these, we can actually abbreviate part of our electron configuration with a noble gas. So we use noble gases since it's a full p sublevel. They have a full valence electron shell, so that's why we use those. But basically, here's what we're going to do. So when you are using this talking is hard. When you're using this configuration, you're going to find whatever element you're looking for on the periodic table, and then you are going to find the noble gas that comes before it. We call it the last passed gas. The gas that you passed to get to that one. So it can't be before it. It's not the closest noble gas. It's the noble gas that comes before on the periodic table. So you're going to bracket that noble gas and then continue your electron configuration until you reach your element. So let's try it with a couple of these, and I think you'll find that it is much shorter to get there. So here we go. All right, so we're going to start with phosphorus, which phosphorus is P. It is number 15. So our last pass gas for phosphorus is going to be one row up from it, Over here, neon. All right, so I'm going to put neon in brackets. And then instead of starting from hydrogen, I'm going to start from neon. So neon. And then my next row after neon is down here, my third row. And I'm going to say, all right, I'm starting there. 3 S sublevel, 1, 2 boxes. And then same thing over here. So keep going until we get to phosphorus. So third energy level, P sublevel, and we go 1, 2, 3 boxes to get to phosphorus. So much easier, right? So much easier. Well, not that it's hard, but it's so much shorter to write it that way. All right, let's do a couple more together. So then our next one would be potassium. Potassium is K right here, number 19. All right, our last pass gas for potassium would be argon. So I'm going to put argon in brackets, and then I'm going to start from there. So basically I've said argon. Next thing is going to be just 4S, and then since potassium is the first one, 4S1. Isn't that nice? All right, I'm going to do one more with you, and then I'm going to leave you guys to do some of them on your own. All right, so silver. Silver is Ag. And it is number 47 on our periodic table. All right, so again, go to the last pass gas. So for silver, that's over here, and it is krypton. So I'm going to put krypton in parentheses, and then instead of starting from the very beginning, I'm going to start from krypton. So after krypton, my next thing would be coming down here to the 5th energy level, S sublevel, 1, 2. And then we're in our D sublevel, and it is going to be 4D. And then we cross 9 boxes. But that's one of our exceptions. So it's going to move one of the electrons from the S orbital. So instead of this being 5s2, it's going to be 5s1 and 4d10. So it's going to move one of those from the s orbital into the d orbital. All right? Okay, guys, why don't you guys go ahead and try to do the last 3 that are remaining as practice. Pause your video, work them out, and then come back here to go over the answers. Let's go over them. All right, so starting with chlorine. So chlorine is in our, right here, number 17. I don't know why I was going to say that 35. It's number 17. So the last pass gas for chlorine is neon. All right, so we start from neon. We get 3s2, 3p5. All right. And then next we had tungsten. Did you remember that tungsten is one of our exceptions that we just talked about? Hopefully you did. All right, so tungsten is right here in our d orbital. So our last pass gas from tungsten is over here, Xe. So put Xe in brackets and then start from there. We get 6s2, 4f14 because of our f orbital there. And then 6s1, and then 5d5 because of that. Electron moves from the s orbital to the d orbital. And last, but certainly not least, we have uranium. It's in our f sublevel. So don't forget, guys, that our f orbital is inserted, that row of that f orbital is inserted right here in our periodic table. So our last pass gas would be radon. So we're going to start here, 7s2, and then 5f1, 2, 3, 4. 5f4. All right, guys, that is noble gas configuration. So it's still the same thing. It's just a little shorter. So now we are going to move in to ions. So the first kind of question, if you guys remember, an ion is a charged particle. We either have a cation or an anion. Cation is positive. Remember, cats have paws, so cations are positive. I know, so funny. And it has lost electrons to become positive. And we have anions. Those are negative ions, and they have gained electrons. So why do these happen? All right, why do we gain and lose electrons? Okay, so ions are formed so that they can have a full valence shell. So there's only one group that won't form ions, and that is the noble gases. And the reason is because they already have a full valence shell. So we're going to be talking about writing the configuration of ions now. And ions change the electron configuration because they either gain or lose electrons. So for example, sodium's normal configuration is 1s2, 2s2, 2p6, 3s1. But sodium with a positive 1 charge, that positive 1 charge tells us that it has lost 1 electron. So since it's lost 1 electron, it's going to, our configuration is not going to be for sodium anymore, but instead it's lost 1 electron. So it's not going to have 11 electrons, it's going to have 10. So we're essentially going to be writing the electron configuration for neon instead of sodium. So it's lost an electron. All right, so now we're going to practice and we're going to write the configuration for the following ions. So for our first one, we have phosphorus with a -3 charge. So -3 tells me that it has added 3 electrons. All right, so if I look at phosphorus on my periodic table, make myself bigger again. All right, so if I look at phosphorus on my periodic table, it's right here in period 3. All right. And with a negative, phosphorus normally has 15 electrons. But if I add 3 electrons, it now has 18 because I've added 3. So 15 plus 3 is 18. So it's essentially like I'm going to be writing the configuration for argon. Okay, so if I'm writing the configuration for argon, start at the beginning. It's going to be 1s2, 2s2, 2p6, 3s2, and then 3p6 for argon. Okay? So now we're going to do bromine. All right, and Br has a -1 charge. So that -1 tells me that we have added 1 electron. All right, come on to our periodic table. Oops. All right, bromine is right here, number 35. It normally has 35 electrons, but we've added 1, so that means it's going to have 36. So really, we're writing the configuration for krypton. Now, since this is a pretty long configuration, I'm going to use noble gas just because I feel like it. So normally, if it doesn't say, you can write any configuration, but just always check what your problem says. It doesn't specify here, so I'm going to use noble gas. All right, so we're writing the configuration for argon. Krypton. Krypton. So my last passed gas is argon. So I'm going to put that into brackets and then start from there. So starting from argon, my next section would be 4s2, and then 3d10, and then 4p6, since we are writing the configuration for bromine with 1 additional electron, which is essentially the same as krypton. Okay, now we're going to do copper. And guys, I'm going to tell you, it's a transition metal, and transition metals are a little bit different. So they're going to lose slightly different electrons. So copper has a +2 charge. That means it has lost 2 electrons. I'm going to go ahead and write out copper's electron configuration how we would normally write it out, okay? So normally copper's electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, what is it, 9? Yes, 3d9. Now, copper has a positive 2 charge, so it's lost 2 electrons. Anytime an element loses electrons, it's always going to lose them from the outermost energy level or the highest energy level. So for copper, that's our 4s energy level, is its highest energy level. So it's going to lose those electrons from there instead of the 3d, because it always loses them from the highest energy level. So it's going to lose those 4s electrons, and then our configuration would end in 3d9. So instead of losing from the d orbital, it's losing from its valence shell. So it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Okay, so you guys have 3 more practice problems on here. Go ahead and complete those. Pause the video, pause the recording, and when you're ready, press play and start watching again to go back over them. Okay? All right, so pause the video, work those 3. Okay, let's go over them. So calcium here has a positive 2 charge. So calcium is normally has 20. Because we have that positive 2 charge, it tells us that we have lost 2 valence electrons. So since we've lost those 2 valence electrons, we are not writing the configuration for something with 20 electrons. We are writing it for something with 18. So we are writing our configuration for argon. So I ended up with 1s2, 2s2, 2p6, 3s2, 3p6 as my configuration there. And very similar with lithium. So lithium, it's right here, normally has 3 electrons, but it has a positive 1. So that tells me we've lost 1 electron. So I am really going to be writing the configuration for helium. So that is just 1s2. Nice and simple. And then the last practice problem you had was for sulfur. And in sulfur, we have -2, so that means we've gained 2 electrons. Sulfur normally has 16, but because it's gained 2, it's going to have 18. So we're going to write our configuration for argon. So I got 1s2, 2s2, 2p6, 3s2, 3p6. All right, guys. Yeah, that's ions. And now Mr. Oglesby is going to take over with the rest of the video notes.
Mr. Oglesby here. I'm actually going to be finishing out this set of notes over electron configuration. So let's do this. So for our valence electrons, let's kind of go through, let's do the electron configuration for each of these ions that we have, and we'll see what we get as a result. So we're going to start with our oxygen here. Oxygen with a -2 charge. That's the ion. Now, the atomic number for oxygen is 8. We know that oxygen normally has 6 valence electrons, right? However, I have a -2 charge there. Anytime I've got that negative charge, that means I've gained some electrons. How many? Well, it's -2, so I've gained 2 electrons. So instead of being 6, we're actually going to have 8 valence electrons. Okay, well, now I need to do my electron configuration. So if I take periodic table, I'm going to start in the top left corner at hydrogen, and I'm going to count across. So 1s, I'm going to go through 2 things, 2. Then I'm going to move on to the next energy level, right? Because I finished out the first. So 2s, how many do I go through? 2. And then normally I would go to P, and normally I would go to 4. However, because it's an ion, I have gained 2 additional electrons. So 2p6. So that's our electron configuration. What's the total number of electrons that we've gained or lost? So we gained 2. So what's our charge? -2. Okay, so what I want you to do is I want you to actually pause your video, go in and do the rest of these. Okay, so pause your video, go in and do the rest of these electron configurations. Okay, so hopefully y'all paused it, but let's take a quick look at these. So I've got magnesium, that's got 12 protons, 8 valence electrons. Electron configuration is 1s2, 2s2, 2p6. It lost 2 electrons, and it's got a +2 charge. I'm just going to let y'all look at the remainder of these so that y'all can double check your answers. Pause the video if you need to check over these. All right. And we're going to go ahead and move on. So what do y'all notice about all of these? What do you notice about, for instance, the number of valence electrons? Well, you should notice that they are all 8. Okay, well, what else do we notice? What do we notice about our electron configuration? Well, the electron configuration is the same. It's 1s2, 2s2, 2p6. So did you notice that before? So what this does is this is actually what we call an isoelectronic substance. Okay, so each of these are isoelectronic with the original thing, with specifically neon. They're all isoelectronic, meaning they have the same electron configuration. Iso means same. So I have iso, same, electronic, so same electron configuration. So it's got the same electron configuration as something else. Now, anytime we're talking about isoelectronic, we do tend to talk about the noble gases. Why? Because your noble gases have a full valence shell, right? And everything is trying to ultimately have that full valence shell. That way it's got a full sublevel, right? Okay. All right, so we are going to go ahead and move on past this. So this was kind of talking about isoelectronic. Again, that same electron configuration, letting you see it. Some other examples would be if I take something like sulfur with a -2 charge, it's going to be isoelectronic with argon. Why? Because they've got the same electron configuration. Bromine with a -1, strontium with a +2. Those are both going to be isoelectronic with krypton, right? So those have the same electron configuration because they've either gained or lost electrons. All right. So the very last thing that we have on our electron configuration notes is the orbital filling diagram, orbital filling notation. So orbital filling notation is basically just a more detailed version of the electron configuration. So we're actually going to start with electron configuration because I think that's a little bit easier in terms of helping y'all see how to do orbital filling, okay? Now, one thing to note, when we talk about orbitals, orbitals can only hold 2 electrons, okay? Orbitals are kind of like slots that those electrons are going to sit in, all right? So if I'm talking about an S sublevel, remember your S sublevel can only hold 2 electrons, so S is only going to ever have 1 orbital, okay? P, if you remember, can have up to 6 electrons. So since each orbital can hold 2 electrons, we're going to need 3 orbitals for the P sublevel. D can hold up to 10, so we need 5. F can hold up to 14, so we need 7, right? So the number of orbitals you need should relate to the total number of electrons you could have in that sublevel. Okay. So again, each sublevel holds, or each orbital will hold 2, but otherwise it's basically electron configuration. All right, so let's start with this sulfur. Now, sulfur does have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p4. All right, so there is my sulfur's electron configuration. So now we're going to do what we call the orbital filling notation. So for orbital filling, we're basically going to write out our electron configuration again. So it is 1s. Now, how many orbitals can the s sublevel have? 1. So 1 orbital. Then I have 2s. So 2s. How many orbitals for the s sublevel? 1. Then I have 2p. How many orbitals for the p sublevel? 3. 1, 2, 3. I'm going to move this out of the way since I'm over here on the right. Then I have 3s. S can have 1. And then I have 3p, which p sublevels can have 1, 2, 3. And you're like, okay, well, I've got those orbitals drawn, but one thing that you'll notice is that I didn't add these numbers. Well, those are very important to actually have. So we need to go back in and fill those in. Well, the orbital filling diagram, what it does is it shows us where electrons sit and how those electrons are actually spinning, because electrons actually spin in place. Well, not in place. Electrons are actually spinning, but they spin inside of that orbital. So for this, 1s, if you look over here, 1s has 2 electrons. So what we're going to do is we're going to draw arrows to represent those electrons. And the arrows have to spin in opposite directions. So 1s, we're going to have one spinning up and one spinning down. Now, those are arrows. You could actually draw them as a complete arrow if you prefer. However, it does speed it up a little bit if you just do that half arrow. Okay, so one spins up and one spins down. Okay, so we always fill 1s before we move on to 2s. And then we fill 2s before we move on to 2p. And then we fill 2p before we move on to 3s, and 3s before we move on to 3p, and so on and so forth. You just always fill the lowest energy level first. Okay, so looking at our 2s over here on the left had 2 electrons. So let's actually erase all these arrows so we can redraw them when we get to them. So we've already done 1s. Now we're going to do 2s. 2s has 2 electrons. So 1 electron spins up, 1 electron spins down. Okay, done with 2s. Now we move on to 2p. 2p has 6 electrons. So I need to have 6 arrows in my orbitals. Now here's the thing. When you put electrons in an orbital filling diagram, they always have to go in single before they can double up. I like to think of this as a school bus rule. When you get on a school bus, you always try to find a seat that sits by itself before you find a seat that is by somebody else. Okay, so you don't pair up before you have to. Okay, same thing with electrons. For electrons, the reason that they do pair up, the reason that they don't want to sit next to each other is because they've both got a negative charge, right? So if they have a negative charge, they're going to repel each other. Okay, so I have 2p. When we start, we always start spinning up. So 2p, we're going to have a spinning up arrow, and then another spinning up arrow, and then another spinning up arrow. We always start with the up arrows, and they always go in single before they double up. So 2p, it had 6 electrons. We've currently only put 3, right? Well, so we got to go in and down arrow, down arrow, down arrow. Now we've got our 6 electrons, okay? And you're like, well, Mr. Oglesby, wouldn't that just be the same as if I did up, up, down, up, down, up, down? Well, technically, yes. However, it's not always going to be that way. And so if you just get in the habit of going up, 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 and then come back in and go down, 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 that's going to be more helpful for you just in helping you remember what to do for orbital filling notation. Okay, so now we're done with 2p, so we can move on to 3s. 3s, we have one spinning up and one spinning down because we've got a total of 2 electrons. Last one, we've got 3p. So 3p has a total of 4 electrons. So here's where you would have made a mistake had you gone in and gone up, down, up, down. That's technically wrong. Why? Because you didn't fill them in single before doubling up. And you're like, okay, well, how would that change anything? Well, let's take a look. So if I go in and I fill in each orbital with 1 first and then come back in and double up, we'll see what it looks like. 1 up, 1 up, 1 up, and then we come back in and do a down arrow there. Well, now we've got the correct orbital filling diagram for sulfur. Okay, so this is the orbital filling diagram for sulfur. Again, we're looking at those electrons and we're seeing 1, what orbital they sit in, and 2, we're also looking at which direction those electrons are going to be spinning. Why do they spin? They spin because we're trying to minimize their repulsion. So if you've got one spinning forward and the other spinning backwards, they have reduced repulsion. That's something that you can actually do if you want something to trick your brain a little bit. Try to take one finger and go forward and the other finger to go backwards. You'll find that it's really hard to do. All right. Okay. So let's do lithium. And then after we do lithium, actually, I'm going to skip on down. Let's do one that's a little bit more difficult. I'm going to do chromium. Okay. So chromium. So chromium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, now this is actually one of your exceptions if you remember, right? And so that's one of those that you actually take one away from our S sublevel and we put it into our D sublevel. Okay, all right. So now we're going to do the orbital filling diagram for this. So I have 1s, S has one orbital, so one orbital. 2s, it has one orbital. 2p, it has three orbitals. 3s, one orbital. 3p, 1, 2, 3. 4s, one orbital. And then, remember when we're in the D sublevel, we subtract one energy level. So 3D, and it's going to have 1, 2, 3, 4, 5 orbitals. Why? Because we can hold up to 10 electrons in the D sublevel. Now, let's take a look at this. So 1s, we had 2 electrons. So 1 electron spins up, 1 electron spins down. 2s, 2 electrons. 1 spins up, 1 spins down. 2p had 6 electrons. So we go up, 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 down, down, down. Okay, I'm actually going to slide on over here just to make it a little easier for y'all to see while I am drawing this. So I have 3s. 3s had 2 electrons. So 1 up, 1 down. 3p had 6 electrons. 1 up, 1 up, 1 up, and down, down, down. 4s, 2 electrons. 1 up, 1 down. And then last we've got 3d, which had 5 electrons. So we need to go back in and fill them in single before we double up. So up, 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 up. That would be your 5 electrons. So this would be the orbital filling. Oops, I made a mistake. Our 4s should only have 1 electron. That's what I get for skipping ahead without looking back. So this should be our orbital filling diagram for chromium. All right. So what I want y'all to do is I want y'all to go ahead and practice on the remainder of these. So do the lithium, magnesium, chlorine, and technetium. Go ahead and pause your video. And then what I'm going to do is I'm actually going to work through these problems real quick. And I'll put them up here for y'all to see the answers. All right. I'm actually not going to do the electron configuration for this because you don't technically have to. So what I'm going to do is I'm going to just do the orbital filling diagram. Okay. So go ahead, pause your video, and get started on that practice. All right, y'all. So hopefully you paused your video, but here are the answers to each of these orbital filling diagrams. All right, this orbital filling notation. So I got 1s2, 2s1. I've got 1s2, 2s2, 2p6, 3s2. That would be my magnesium. Again, check those arrows. Make sure you've got them in the right place. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p6. Sorry, 3p5. I made a mistake. Let me fix that real quick. Boom. And then last one I've got is technetium. I've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and 4d5. All right, y'all. So that is it for our electron configuration notes. Please don't hesitate to reach out if you've got any questions. Otherwise, y'all have a great rest of the day. Bye, y'all.